my attempt is to cover discretized state space machines and then move on to two different types of discretized state space machines. One is S4 and the other one which gained a lot of popularity, which is Mamba. But just for some recap sake, what we started on with when we discussed state space machines as an alternative way of modeling language, we looked at language as a diffusive field, right? So instead of looking at in a sequential model, let's say like Rakov or Arden style models, so instead of looking at the updates, that's the information update that happens at every time step when a new word comes in, which is discrete, we look at it more like there is a continuous evolving flow of the different aspects of semantics as a new word comes in. So the standard SSM ODE, or the ordinary differential equation, is that if you have a state, let's say x is the state, which is, or the history, let's say the memory that is continuously evolving, and if you have to look at the change, the rate of change of that memory, that is given by this equation axt plus where a is a transformation matrix, and it's added to BUT, where U is the update information, the new information that is coming in, right? So XT is the latent semantic field. AXT means how that field drifts or decays. And again, it may not necessarily decay all the time. It can shoot up as well. BUT is how the current state nudges or perturbs this particular field. So I gave you that analogy of, imagine that this room is filled up with fluid with different viscosity and density at different places, and you're trying to swim. You're drifting through this room, and how you would drift at different time steps at different positions. So think of it like that. So or another way of looking at it is that as I am speaking, there is a thought process going on. You're trying to understand me, but this thought process is continuous. So even if I pause, your thought process is still moving, and you're trying to figure out what next, right? And you're trying to, and the more I speak, the more you will be able to associate that thought process, the direction of that thought process, towards what I am going to say next. So then once you model the state, then you look at the contextual embedding, which is YT, as yet another matrix called C, which is CXT, and DUT, where D is a learnable matrix applied on the incoming new input, right? So the goal is to express xt plus delta, which is what is that? What is, if there is a delta shift in time step, what would be the new state? The new state is xt plus delta, right? In terms of xt and in terms of u. And then later on, obtain a per token update, which is the discretized version, right? So if you solve the continuous SSM ODE, you would get this solution, this closed form solution. So x of t plus delta is e raised a delta xt plus an integration over e raised a tau, where tau is the history, the entire trajectory, b multiplied by b of u of t plus delta minus the tau, integrated over 0 to delta, which means that particular delta interval. And where E of A delta xt should be understood as the drift of the existing memory. The integral is the accumulated input effect over the interval. Right, so this is the continuous solution. I gave, I'm not going to go through this, but last time I discussed a little bit about how to solve this. In this lecture, in this slide also, I have given a slightly neater and cleaner version of how to solve this particular equation, and how to from the original ODE mix, how do you get the final closed form solution over here down there. That's basically the Duhamel's formula. But then this is continuous time, right? Okay, you can go through it later on. I mean, it's pretty simple calculus. And also we discussed last time that how to interpret the structure of A. So if we assume that A is diagonalizable, right, then we can eigen decompose A into V, which is the eigen matrix and the diagonal matrix lambda and V inverse. And but then the eigenvalue, what is the meaning of the eigenvalue lambda? The meaning is that it reflects a particular intensity of a particular aspect, semantic aspect that is captured by A, or a semantic direction that is captured within the particular history that is captured by it. So the history has all different aspects. So let's say if I say John loves Mary who lives in New York, then as you approach who, there is a meaning drift that is going on from John to loves to Mary and so on. But then the meaning itself has all different sorts of aspects. One aspect can be the proper nouns, how the proper nouns are flowing. Another aspect can be the verb phrases, how the verb phrases are flowing, whether their intensity or whether their influence going forward is dying down or increasing or whatever, right? So there are all different aspects. So that each aspect are the eigenvectors, and the corresponding intensity and or how that actually evolves over time would be the flux in the eigenvalue, right? So and if you we also saw this, that if you understand the eigenvalue as a complex number with a real part alpha and an imaginary part beta, then you can rewrite E lambda it for a particular aspect, for a particular aspect or I. You can rewrite E alpha it as lambda it as E alpha it cos beta it plus I sine beta it, right? And we also discussed that the real part, which is the alpha part, tells you whether it's an exponential growth, right? And whether it's an exponential change, and the change can be a growth or a decay of whatever is the amplitude. And the imaginary part is or the beta part will tell you the oscillation. And by oscillation, what we mean is the recurrence of a particular pattern. So whether the semantic pattern will again reoccur over time. So that is what the oscillation would mean. Ideally we would love alpha I to be less than 0, in the sense that the memory should decay, the memory should eventually fade. But this word eventually is very important. Please note that it should not drastically decay. It should eventually decay, right? So if alpha I is equals to 0, that would mean that memory persists. It just remains the same, right? If alpha I is greater than 0, it would be like it's booming. It's almost like it's, and if that happens, then what happens is down the line it will suppress all other aspects, right? It becomes the dominating semantic information. And if beta is not 0, which means if lambda happens to be complex, then there is a recurrence of theme. Let's say the subject verb object pattern is recurring many times and so on. So together, each eigenvalue encodes how fast and how rhythmically meaning evolves. So that's the interpretation of continuous state space machines. So, but then if you look at it, you see that by definition, A is time invariant, which means whatever you have within A, that doesn't evolve over time, right? But then we are all the time talking about evolution, right? We are always saying that, okay, how the semantic the semantic drift is evolving over time, which means how lambda and all of that is evolving over time. So how can it be if A is time invariant, then your lambda and V is also time invariant, right? So what do we really mean by evolution over here? So if you look at it, you'll see that the eigenvalues and the eigenvectors, they don't change. They are fixed because A is time invariant. But what really changes is this particular factor, which is E raised lambda I t. Why? Because of t. Because there is this t or delta associated. So changes with time. So time appears in the exponential, and this drives the decay of the oscillation. Okay, this is called the mode. So while lambda for a particular A doesn't change, but since the t is evolving over time, that drift is seen. Okay, so and thereby, because that happens, thereby all the associated coefficients like the real part and the imaginary part associated with that t will also, will push that drift to happen. So how state evolves? So if A is diagonalizable, which means A equals to, let's say, Q or V, whatever notation you choose to use, and if you define them, which means you make a change of basis. So if you define the modal coordinates in a way which is basically change of basis, and instead you use ZT as the same as what happens if you do if you apply an inverse transformation on xt, then the initial x dot t, which is dx by dt, that equation changes to z dot t equals to lambda zt plus q inverse b ut. Now this is important, and you might be saying, why am I even doing this change of basis? I'm writing the same thing. Why should I even be bothered about doing this? We'll look at it later, like why this helps. So, but one thing very interesting that has happened is, instead of using A, you are using the diagonalized version, which is the diagonal matrix of A, after the decomposition happens. Of course, here, what is the assumption? That A is diagonalizable, right? So in the Z form, in the change of basis form, you don't have to deal with the entire A as such. You're only dealing with the diagonalized matrix, which is lambda. Okay, so change of basis separates memory into independent modules because it's a diagonalizable. It's a diagonal matrix, right? So the diagonal matrix will contain what? The eigenvalues of each of the eigenvectors, right? So that's what it represents, and they are independent. So it kind of separates out those independent modes, and and each eigenvalue lambda I defines a distinct time scale, and the inputs enter via B and are projected into these modal directions through Q inverse B. So that's the interpretation. So dynamics of each mode. For mode I, extract the ith component, you can do that, and that would be like the capital V, you are extracting each of the each of the row vectors of those of that B, sorry, the column vectors of the B, and then you are essentially that changes, that Z form changes into lambda I Z I T plus B I transpose U T, where B I transpose U T would be E I transpose Q inverse B, right? So it gives you a much neater version of that ODE in terms of Z, and then you can if you integrate over on both sides, you'll get ZIT equals to the solution, the closed form solution, E lambda I T minus T0 ZI T0 plus E lambda I T minus T tau BI transpose U tau over T0 to T. And you can set T0 at whatever time point you want, and this T minus T0 is the delta. So E raised lambda I T minus T0 is basically that drift during that time interval. So how existing memory decays or oscillates. And BI transpose U tau would be how new input excites mode I. Now, one important thing to understand over here is when we say U tau, we not only mean the particular U or the input at that time point, the current time step, but we also mean what all input has happened over the trajectory so far. So U tau represents, while UT represents a particular time step, but U tau would represent that entire trajectory, and you are bounding that trajectory between T minus T0. So that's what has happened. So you are only interested what has happened between T and minus T0, or in terms of the U. So accumulation, and if you unroll the particular integration factor, you'll see there's an accumulation of the dynamics over time, which would mean that what you are doing is you are basically saying that this T minus T0 can be written as, let's say, delta T, and then you can look at the integration from this point of view, where it's a summation over k equals to 0 to t minus 1 e raised lambda I delta of t minus 1 minus k multiplied by bi transpose of uk, right? So we'll see how this works out, but again, it's the interpretation being the same, like e raised lambda I delta t minus 1 minus k would represent the fading echo from all the past tokens in that time interval, within that time interval. And bi transpose uk, how strongly token uk, particular that token uk at that time step k, excites mode I. This is for one mode or one feature, right? So there are multiple such features or modes. So, and then you can reconstruct everything by multiplying zt with q, which is the linear transformation of zt via q, would give you back xt, and then yt would be capital cxt, which is basically cqi of zit over all the modes or features. So again, the linguistic representation would be the eigenvector are the semantic axis or the directions, like topic, phrase, connectors are the like who, which, what. So those sort of connectors, directions, and so on and so forth. Lambda I is how fast or how rhythmically the semantic phrase fades or oscillates. Bi transpose ut would be how much the current word injects energy into that particular semantic index or semantic axis. I, and ZIT would be current strength of that particular memory mode. E lambda I over that t minus t0, which is the delta, that is the memory persistence or decay or recurrence, whatever that is, over that time interval. So why discretization is needed? Now this is all continuous. So if you look at how language works, which we discussed last time also, language works in discrete, the U or the input comes in discrete time intervals, right? Like when you say John loves Mary who lives in New York City, the discrete tokens come at discrete time steps, right? So when we say that we need to discretize a continuous SSM, what we really mean is we don't go back into the world of Rakov or LSTM. No, that's not what we are trying to do. What we are trying to do is we are trying to, it's almost as good as saying that, okay, there is a continuous flow of semantic drift happening with new and new input coming in. But the problem with continuous SSMs are continuous SSMs assume that your input is also going to be continuous over that continuous drift. So you're continuously, as if like I'm continuously speaking, or your signal that is coming in is also continuous. So but then that's not how language works, right? So then what we do is imagine that while the memory is continuously drifting, we are taking snapshots, like snap pics at different time steps. And then we are updating that snap and then let it flow and then again taking a snap. So basically what we are doing is sampling, right? So we let the continuous flow to happen, we let the drift to happen, but we sample that particular state, at every time step. So what we want to do is, instead of writing xt, dx by dt as axt plus, but, we want to write xt plus 1, which is the next, what is going to be the state at the next step. We want to convert that equation, the ODE, into this update equation. That is what we want to do, and we will see how we do it, right? Which is xt plus 1 plus a bar, some a bar, which will give you that snapshot of a, the snapshot of a at that particular time point. A bar xt plus b bar ut. That the b bar is also the snapshot at that particular t, right? Where a bar is equals to ea delta t, preserves semantic drift and oscillation. Okay. So this is what we do not want, because that's not how language works. The expectation that there will be always a smooth input flow, right? And that is why the discretization is needed. Okay. And what we are doing is we are sampling. So the trick, we call it zero order hold. So the trick is that we, as we said that earlier on, we used to look at u tau as whatever input has happened over the entire trajectory, the entire continuous u, the supply of u over that entire trajectory tau. We look at that as no. That is as good as saying what has happened, what is happening right now. So we approximate that to ut, over the time interval t to t plus delta. So the tau that was going on from between t to t plus delta, we say that no, if delta is small enough, we can approximate that tau to whatever just happened right now. So this approximation is called zero order hold. Okay. And then if we plug that ut instead of u tau, it now becomes ut. So then we can bring that ut outside the integral over there in that UML's closed form formula, and then it becomes, and then we just write e of a delta xt as a bar, and we write that integration as b bar. the integration part only, not ut, just the integration is b bar. And then what we do, we then have and then we can get this particular update form, which is xt plus 1 is as good as saying e bar xt plus b bar ut, right? That comes straight from Duhamel's formula, but we just plug, it's straightforward, we just make that assumption of zero order hold and we just get this. Okay, so now what we got was from flow, we got a token level discrete sampling, right? So we got discrete updates. So basically, if we again look at what happens in the modal level, because why we wanted modal? Again, because we, instead of A, we love the lambda or the diagonal matrix more, because that is a cleaner way of understanding what really is going on and easy to compute as well, because it's just a diagonal matrix. So if we have to write it from a diagonal matrix point of view, we have to again go back to the changed basis or the z form, right? So we then basically what that z form becomes is that zt plus 1 is equals to e lambda, where lambda is the diagonal matrix after you do the eigen decomposition, and multiplied by delta zt plus q inverse b prime, b bar ut. So that's what happens for a particular aspect or mode, component wise, which means it becomes this. Okay, so now if you have to have a numerical solution of this, then how would you solve it? You just use the matrix version of the Taylor expansion of the Taylor series, and e prime would be, a bar would be ea delta, that is el delta would be I, the identity matrix, plus a delta plus a squared delta squared by 2 factorial and so on. And b, and therefore b bar would be, which is the integration of a, e raised a tau b d tau, which is going to be this. One important thing to understand, that b is dependent on a. If you look at the equation of b is not independent of a, b is dependent on a. So how the new input is going to affect the old memory is going to be influenced by how the old memory is being captured, how the essences of that memory is being captured, which is inside A. Okay, so B accumulates input influence within the step. So this is just if you do not, for some people, if you do not understand how this is working, and I gave you some notes, sort of like how this works. So what exactly is discrete evolution? So as I said, tokens arrive at discrete time steps in language. So t would be 0, then delta, then 2 delta, then 3 delta, and so on. So each token samples this continuous semantic flow. And but if the question is that how does this sampling affect the evolution encoded by lambda equals to a or alpha plus I beta, because that is continuous, right? So that was under the assumption that everything is continuous. So when we move from the continuous evolution of E lambda t to its discrete version, which is E lambda delta, we don't really lose much, so the sampling does not affect the semantic dynamics. So because if you say lambda bar is equals to E lambda delta instead of E lambda t, you would end up getting this, right? This form. If you consider that lambda can be a complex number as well, and the interpretation is that E raised a or alpha delta is how much meaning is retained or forgotten between two words or two tokens. Cos b or beta delta plus I sine beta delta is that fluctuation basically, because the sinusoidal curve, right? Or the recurrence, and delta is a sampling interval between tokens. You can consider delta to be 1 for language model. So eigenvalues dynamics are preserved in the sampled form. So why not be happy with, now a question can come, okay, we are done, probably we are done. So we have a full form solution, we have a numerical solution, we can just plug that in, code it up, and we are done in terms of getting contextual embeddings, and then we can put a head over that and do whatever next word prediction or classification, whatever that is. So long we get a y, which is basically the contextual embedding at every time step, we can finish the story here. Why do we even move forward, right? So if we for now for the discussion's sake, if we just say that okay, we will just stick to yt is equals to cxt, and we leave the dut aside, because the dut term doesn't, it's just basically the static meaning of that word, not the contextual meaning. It's not linked up with the memory. It's just that particular word coming at the particular time only. See, C is linked up with xt. C is linked up with the memory. So if we just look at what's going on over there, so each new token ut that comes up at particular time point is basically updating a prime xt via b prime, or sorry, b bar, because b bar is again associated with a bar, right? So ultimately you are updating the memory via a bar only, because as I said, just so that you don't forget, so b bar is basically your is dependent on a bar only, right? So basically what you're doing here is you are updating through a bar. But this recurrence is inherently sequential, which means you can't work, you can't update xt if you do not update xt minus 1, and you can't update xt minus 1 if you do not update xt minus 2. So it has to, one has to follow the other, so it's sequential, right? We must process one token at a time. So this hides how much influence each earlier token still has, which means the strength of, let's say, the conditional independence that you were assuming in transformer based, self-attention based models, where John can independently come and influence who, that is kind of going, because you're constantly saying that no, who is going to be influenced by the state, the previous state only, which encompasses or accumulates John loves Mary all together, like compressed together, right? And what you're saying is that who is influenced by that compressed state. So which means that there can be a possibility that John fades away and John never gets to influence who, right? So this may hide how much influence each earlier token still has, because it's an accumulation. It's like a snowball. So the same problem that LSTMs also would have. So what you do is you translate the sequential memory into what we call a convolutional memory. It's a trick. It's a basic algebraic trick. Simple. So what do you say? You say that okay, xt, if you unfold or unroll xt, you'll see that xt is basically a summation of all the prior a t minus 1 minus I b bar ui, right? Because xt contains xt minus 1. You can rewrite xt minus 1 in terms of a bar, b bar. That again contains xt minus 2, and you can keep on doing that and keep on going till the beginning, right? So again, you can unroll that and you can go till I equals to 0 till the previous point, right? And you can rewrite xt as this summation, right? And if you now and then you can rewrite that summation as ut minus, you can just change the subscript, and you can say that you write ui as ut minus k, where k is equals to 1 to t, and you get this really nice neat form of a bar raised k minus 1 b bar. And then what you do, you plug that into your cxt. So you have the C matrix, and then in x, instead of x, you plug this summation. So C multiplied by the summation. Now you can bring the summation C inside the summation, which is what you are seeing over there. So C multiplied by this summation, and you can bring the C inside the summation. So you get C a prime a k raised to k minus 1 b b bar, not prime, ut minus k. This summation is called the convolution. Okay, so this is called the convolution memory, this entire summation, right? So this operation is called convolution. And in short, you write it as k with the convolution operator u on till that time point t. So yt, which is the contextual embedding at that time point, the contextual embedding of the word at that time point would be the kernel k. You just make a shortcut note or a notation of that of this kernel, which is c a bar raised to k minus 1 b bar. You just say that, okay, let that be k of k, basically, till that time point k. So for every time point you have such a k. So when k is equals to 0, k is equals to 1, you have c b bar. When k is equals to 2, you have c a bar b bar. When k is equals to 3, you have c a square bar b bar, and so on. So so you get a whole bunch of kernels for every time step, prior time steps. So these are the kernels that you have. So when for John you have a particular kernel, for Loves you have a particular kernel, for Mary you have a particular kernel. And when who comes in, who looks at each of these kernels, picks them up, and then what it does, it uses that kernel and sums them over for every u, which means it sums. So John's kernel gets multiplied with John's embedding, plus Love's kernel get multiplied with Love's embedding, plus Mary's kernel get multiplied with Mary's embedding, and you sum that up, and that would be, and then you multiply that entire thing with C. So this is what we call as the convolution, and in order to write it neatly, we use the kernel k. Now if you look at it, something very interesting is going on. So why to translate it into a kernel form? So basically it's a very neat way of encoding how what is the effect of a token k steps ago decays or oscillates before reaching the present. So that's basically what the kernel would mean. So what's this effect? What's this influence? Now if you look at, so as I was saying, so k0 would be let's say this, you reach till the end. John loves Mary who lives in New York City. Now when you are at city, that's K0. And then you go back. Then you have K1, K2, and you keep on going back. And you have K3, K6, and so on. Right? Now, one important thing is that if you look at this equation, if you look at this equation, you see there is an uncanny resemblance, with what happens in transformers in self-attentions. So if you look at self-attentions, you'll see that, and if you try to compare this equation with self-attention, you'll see that in self-attention, what is going on? Like there is a percentage that is applied to the value or the V, and you sum that over all the V's. Now V is basically your neighboring or the word that is coming, the words that are associated, or basically the words that are neighboring to that particular one word. Now if you look at a causal model, then you only take all the words that have happened so far, which means all the backward words, and you take the percentage of every word that has happened so far, and you add them up into the new, to get the new contextual embedding of the new word, right? Think of this K subscript K as that percentage for each of the words. So what is that percentage influence coming from John? What is that percentage influence coming from Loves? What is that percentage influence coming from Mary? And so on into, let's say, city of New York City. So all the incoming edges. So this summation essentially, which is the convolution, it has a very neat analogy with what happens in self-attention. The only difference being the way we do self-attention, the K over there, the kernel for self-attention is basically a dot product between the query and the key. Over here, you don't have that concept. You're just using the A matrix and the B matrix, the discretized version of them, in order to create this kernel. So again, going back, the kernel is basically this, where, right? And because of the exponentiation, because you see that as you go back in time, it becomes a square, a cube, and so on. So basically the effect is trying to decrease the effect in an exponential manner, right? So as you go back, but the B can inject that information back again. So kind of like what Raku was trying to do with the alpha and the beta, where alpha was doing the exponential decay and beta, which is the update gate, was trying to again bring back some of the information if it is required. So computing this is going to be expensive. Why? Because for every YT you would need to do this summation, right? And there are so many YTs. So for each one of the YTs, if you do one summation, there are two loops going on, right? So basically it becomes big O of t square, where t, capital T, is the sequence. So can we do it faster? So this is the real deal. So instead of looking at, so one way of looking at every word is like, every word is like an echo. So just like how I'm speaking, so as I speak one word at a time, there's an echo going on in your thought process. So which means you are not really forgetting the word that I'm saying right now, but eventually you will forget some of the words that I am saying in my earlier part of my discussion. So you will only attend to the most recent set of words, but at the same time you won't forget the theme of this entire talk when this discussion started. So think of it like there is an echo of every single aspect of the words that I spoke before, although you may not be remembering concretely what those words are, but you remember the essence. Essence means the eigenvectors. and how much you would remember is how the eigenvalues are fluctuating in terms of the mode, right? So this is the time domain. So long as you are in the time domain, you cannot get past the quadratic complexity. Okay, so what we do is we say that, okay, let us first imagine embedding as a signal that is being injected into the overall larger signal of memory, like how the thought is evolving. So let's look at, so it's almost like, just like I am talking and you are processing it, think of the model as looking at a text and processing it. There is a thought going on inside the model. So think of it like that. Maybe that will be helpful to understand what's going on. And now every embedding that is getting injected, think of it like a signal that is being injected, new signal getting added to the already existing signal. Now there's a whole lot of echo going on right now, because different words with their different aspects having their own echo. So it's like an echo chamber. So everybody, it's like a conference and everybody is trying to talk with everyone. So think of that situation. Just imagine for now. Then what we can do, if we can imagine that situation, like, in a wave way, if we can start thinking in a wave way, then we can apply something very interesting, which is the Fourier transformation. So every signal or waves, we can look at it as at a Fourier point of view. And we can now convert the echo to a rhythm. And we can split these rhythms. So the overall signal, we can split it up. And we can split it up like this. Let's say that U is one particular signal, the echo, and we can split U into its corresponding frequencies sort. So to say that every frequency is a particular aspect of that particular word. So every word has all sorts of aspects, right, in terms of the linguistic meaning. So what you are doing is you are splitting these aspects, which earlier used to be the eigen vectors. You imagine where there were so many different types of lambdas, and you were splitting the lambdas for every single component. So this omega is one such component, but now we are looking at that component from a wave point of view, right? So C omega would be how strong the rhythm is, and E raised to I omega t would be the frequent, the particular discrete, the discrete transformation. And if you sum it up, you should be getting the original ut back. So that is the Fourier transform, right? So making the quadratic convolution fast. Now what you do, you actually then you apply a particular technique called the fast Fourier transform, which converts your convolution into a simple multiplication. So this convolution right now, what you have in blue, so that's the convolution, that's the summation, right? The summation of all the k's. So you can rewrite that as in terms of the fast Fourier transformation of the k, which is the kernel, the u, you multiply that, like a Hadamard multiplication, and then you get back the y using the inverse fast Fourier transformation, right? So in time domain, you have to do the summing. But the moment you get into the frequency domain, you can do this FFT and by just multiplying the rhythms, which is much faster and will give you something like a t log t complexity instead of a t squared complexity. And if I have to move into like how this happens, which is basically the FFT operation, then if this is the convolution, the one in blue, then what you do is you just say that, okay, your Fourier for a particular component omega would be across all the time steps would be ut e of e raised minus I 2 pi omega t by t, which is the basically that every time step can be thought of like the time period across, right? And then you try to understand whether it's going to be a high frequency wave across the time period, or it's going to be a low frequency wave. And the idea is, if it is a low frequency wave, then your that particular memory persists over time. But if it is a high frequency wave, then your memory will not persist that much over time, right? So whatever you want to remember through time, that the frequency should be lower. So that is the idea. So this is the element wise multiplication, and you apply the inverse to that to get yt. So replaces the t square complexity with t log t complexity. So FFTU, what is the linguistic interpretation? This is, I guess, the most important part that you should take note of. So FFTU is basically decomposing the sentence into semantic rhythms, like slow rhythm, as I said, to capture topics, because topics you have to remember. You can't forget the main topic. So like John, Mary, so those should have ideally slow rhythms. Fast rhythms capture short syntactic ripples like in, who, and so on. FFTK, what does that mean? It means that it encodes the model sensitivity to each rhythm. So which means it will decide how much of the amplitude I need to have. For every frequency, you can increase or decrease the amplitude, right? So FFTK would decide on the amplitude. So there are two knobs. One is the frequency knob and one is the amplitude knob. So the frequency knob is decided by FFTU, and the amplitude knob is decided by FFTK, or the kernel, right? So which is that percentage that's coming, that's the amplitude basically. So whether to amplify or to damp, right? And that's the beauty of it, because otherwise, if you look at LSTM, Rakub, or others, I mean, there was no guarantee that it will always be a decay. There was no way to figure out how to also increase if needed. Now over here, you can increase, because even John can have a very strong influence to, let's say, New York City, if its K, FFTK, is high. Okay. So and the analogy that I found was like, rather than replaying every echo word by word, you do an FFT which lets the model play the whole harmony of context at once, at one go. And you can look at the derivation later on. I mean, I have given you some derivation as I like. How do you even get to that? From the discrete, from the discrete convolution, which is the summation form. How do you even get to that FFT form? So that derivation is given over here. It's not a very. It's quite a simple derivation. It's just that you have to make sure that since FFT is circular in nature, so you have to break the circle by adding some padding so that you make it causal. Why? Because the standard FFT will also look ahead. A causal language model cannot look ahead, right? What is upcoming, it should not see what is the upcoming words. So you just have to put some padding. So basically, when we say FFT of K and FFT of U, we pad it up and then do the FFT, right? But the derivation you can look at over here. It's a very simple derivation of how we get to that FFT of Y is the same as FFT of K, Hadamard FFT of U. So now the eigenvalues, as you know, are basically what is the relationship between the eigenvalues that we used to see before, right, versus this omega. So the kernel, if you look at the kernel is C A bar raised K B bar, And if you look at if you replace that with the eigen form, which is the lambda form of the q, which is q e lambda delta q in q inverse, and if you just plug that a bar with this, you get this, right? And which means your kernel is directly proportional to the 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 real part of alpha and the imaginary part beta in this manner, if you look at it. So basically that's the equivalent, that's sort of the relationship between the frequency version and the time version. So the frequency domain view would be now, so for k from a frequency point of view, which is omega point of view, would be c e of I omega, the identity matrix I, minus a bar whole inverse of b bar. Okay, so whatever is the imaginary part, which is the beta part, that corresponds to the frequency omega in the Fourier space. Whatever was alpha, which is the real part, that is basically the decay. That still remains, the interpretation is just the same. And the eigenvector, whatever was the eigenvector qi, that gives you the semantic direction of the oscillation, that also remains the same. Okay, so putting it all together, you have this. That's the connection to the FFT, right? Okay, so again, we, just so that you understand where we started off with. So this is the continuous version, and so this was the continuous ODE form, and the eigenvectors and eigenvalues would mean this, right? So the real part would mean the rate of memory decay, and the imaginary part would how memory recurs over time. So discretization, we saw how to do the discretization, the zero order hold assumption, and we then said that we don't want the sequential memory, we want to rewrite it by unfolding or unrolling as a convolutional memory. Then we get this beautiful, nice analogy with self-attention, the summation of the kernel multiplied by the U, right, in that form. And then we say that, okay, if we are to make it even faster, we can actually do that. Instead of summing it up, we can look at everything as a wave, and then we can convert it into a Fourier transform, and then we can do this inverse Fourier, fast Fourier transformation to get the y back, right? So this is the neat relationship. FFT of y is the same as FFT of k, Hadamard FFT of u. So now the question is that, is FFT based kernelized discrete SSMs enough? Should we stop here? Again, the same question, right? So we got it right, so why not just stop here? So the problem that we have to, kind of the concern that we should have at this point is that, okay, we got A bar, we got B bar, but we don't know how to create that A bar and B bar. We know at least one thing, that it has to be diagonalizable. The A bar has to be, otherwise we won't get the lambda matrix or the diagonal matrix. So it has to be diagonalizable, right? So that's all we know, but we don't know how to diagonalize, and whether we should just do a straightforward eigen decomposition, will that be good enough, or whether we should do something more than that, right? So the answer to a straightforward eigen decomposition is like, no, it's not good enough. It's never going to guarantee you stability, in the sense that you do get the discretization, so you do get how we should step forward as we go over time. So how the changes happen, that we understand from this equation. But what we don't understand is that whether each step, whether each word that is coming in, whether that would maintain the gradients, whether the gradient should not vanish or whether the gradient should not explode, whether those things are going to be maintained or guaranteed. That is not guaranteed, and we'll look at why that is not guaranteed. Okay, so let's say the instability in terms of learning the ABC matrices. So even after you have done this discretization, right, so the stability condition, if you look at it, what is the stability condition? That your lambda of your E bar, the magnitude of lambda should be less than 1. Otherwise it starts, it can explode. So, but during training there is no way, because if you just do an eigen decomposition based modeling, there's no way. Your eigen decomposition doesn't necessarily guarantee that your lambda has to be, the magnitude of lambda has to be less than 1. There is no real guarantee, right? So your gradient based training on unconstrained ABC can easily push the eigenvalues outside that unit circle. So exploding, it can easily explode, and sometimes it can also vanish. Vanish, we will look at the cases where it can also vanish, but it can easily explode. As an example, like some words may dominate memory endlessly, like as if like the echo is happening, or is continuously happening, John, and so on. And it's kind of, if you look at it from the Fourier point of view, that wave is so much predominant and the other waves are getting suppressed. So that should not happen. So now the other problem that can happen is that if lambda I is less than 1 also, still the memory decays exponentially, because it's e raised lambda I delta multiplied by delta, right? So that e raised lambda I, it can exponentially decay, and then thereby what will happen is your gradients will vanish. So discretization does not remove this exponential sensitivity, whether growth or decay, both ways, right? So the linguistic analogy is that Mary can very quickly fade instead of gradually fading. So the third problem is the computational cost of the diagonalizability. If you have to make a diagonalizable, you have to diagonalize it. That has its own computation. These are not small matrices, right? So although it looks like, oh, your FFT just takes t log t time, but in order to get to the diagonalized version of it, which is the lambda version of it, that itself will take some time. And then only you can apply because the FFT is applied on the kernel. The kernel comes from the A, right, or the lambda, whatever. So eigen decomposition alone will not help. That is the thing, because the V or the Q, whatever that notation you use, is not necessarily be orthogonal. They might be independent, but they not necessarily be orthogonal. And what you want is orthogonality. What you want is that every aspect should be independent of each other, completely independent, without every aspect should have a different direction of drift and should not have a component on each other. So that's what you would want. So instead of that, what if you can do something like a spectral decomposition? But for that you need to have an additional condition, that your A must also be a norm matrix, which means A conjugate should be equal to A conjugate A. So that in the complex space, or at least in the real space, the transpose A transpose should be equal to A transpose A. So that condition has to be there. Only then you can make sure that if you do the spectral decomposition, which is a particular form of eigenvalue eigendecomposition, but where you can now guarantee that your eigenvectors will be perpendicular to each other. So if you do that, so basically you need yet another thing, which is you need to make your A norm. But how to do that now? So you need to have this norm. So the takeaway is that structure is still needed, which means you cannot just leave A to God's will and make A get trained via the data, because there's no way you can guarantee these things not to happen, and you will again fall into the complaints that you used to get with LSTMs and RMN style models, that the gradients are exploding or vanishing and so on and so forth. You will again get the same set of complaints. So if you just leave it just like that and leave it for training, so what you're doing is you're saying that okay, we need some sort of a regularization. So we need a structured A, designed A, with eigenvalues guaranteed to stay within the stability region. And we need efficient spectral computation of KK, or the kernel. And that was the motivation for the S4 model, right? Again, remember what is the requirement? The past has to be remembered if it is needed, and even if it is long time ago, it still needs to be remembered if it is needed, without the gradients to explode or vanish. Update the memory online as each token arrives. Be efficient on long sequences. Be interpretable. The final thing is also very important. Be interpretable. Okay. All right. So then, this paper from Stanford. I think this was published in ICLR 2021 or 2 or something, and this paper came up, how to train your hippo. So this was basically a paper, the takeaway from this paper was basically how to structure A so that the eigenvalues remain in the stable region. So they came up with this technique called hippo, okay, which is a particular way of, and we will look at that, but the idea is that instead of looking at the entire past, which is u tau means the entire past sequence, instead of looking at that, you make a summary of that. So instead of going long past the entire long horizon, because that's too long, you make a summarized version of the information in that entire long past sequence. You make a summarized version of that. So, and then what do? You take out the principal components. The principal components, which ideally should be orthogonal to each other, which means one component should not be a reflection of the other component. You take the principal components of that summary, and then you come up with this form of a state form, where the CK is, let's say, the state, the running state or the running memory, the summarized version of it, and that is approximated as u tau multiplied by pk tau, where pk is basically the principal components, the principal wave components, essentially, right? So it's like a smooth wave, a smooth shaped wave, where every pk is orthogonal to each other. These shapes are chosen to be orthogonal, which means they don't overlap or interfere with one another. From a wave point of view, there is no interference. Okay, so, and C0 would then be your average topic, C1 your more recent ones, and so on and so forth. So as you increase your C at every time point, you get more finer short-term details. So that is the idea. So which means your P0 is going to be the broader topic, would represent the P0 wave would represent a broader topic, P1 would represent a bit more detail, P2 will represent even finer details, and so on and so forth, right? So every P wave which you are integrating over represents the detailedness of whatever is going on in the memory, right? But it's a summarized version. The summarized version is more important, right? So that is how that is the key philosophy of Hippo. Summarize the entire past with few running summaries. So these are the summaries, and they should be orthogonal. Your summary should be orthogonal with specific trend in the past signal. Okay. So Hippo, or what we call as high order polynomial projection operator, so that's what they proposed, is basically this only. So the linguistic interpretation is, think of Hippo as keeping a few dials, like a clock moving, lot of clocks moving, and one clock, the slower clock, would be about the broader topic. The medium one will be for, let's say, phrases, noun phrase, verb phrase, and so on, and the faster ones will be for the connectors. So why orthogonal polynomials? Again, memory channels, these clocks should not interfere with each other, so the memory channels should not interfere. So, and what happens is, because if you, instead of A, if you take A Hippo, the Hippo version of A, then what happens is the real part of your lambda is always going to be stable. So each dimension acts like a different memory speed, I, the dimension of the component, and the goal is to design this A Hippo and thereby the B Hippo. So all these tracks, all these signals, they become the coefficient, so without reintegrating from scratch. So we wish to maintain this, and we wish to get something like this corresponding. So the same old principle, where instead of X they used to call it C for some reason. You can think of C as X. So XT A Hippo, XT plus B Hippo UT. So now everything is hippoized, sort of. Okay, where A Hippo is for a matrix of K cross N is going to be something like this. If you look at the diagonals, so it's going to be something. So if N is less than K, then your diagonals will look like this. If N is equals to K, your diagonal will look like K plus 1. If N is greater than K, your diagonals will all be 0. So usually your N is lot less than K. So how to get to that? I mean, I'm not going to go into the details. You can look at the steps, like how to derive this. How do we even get this square root of 2k plus 1 and 2n plus 1 and so on? So you basically think of this the principal waves as a Legendre polynomial, and that was how they came up with this thing. They assume that these principal waves, which are orthogonal to each other, they are Legendre polynomials, defined on over -1 to 1. So which means that if you integrate each one of these, the k and the n's, you get something like that. And then if you define it over 0 and 1, because that is our delta, and if you change the variables, you get something like this. And then if you normalize for the normality, you get every component P becomes P bar, and that is basically this. And and then so you can look at this thing. So so the so then you can, so I'm skipping the details of the, I've given you the details of the derivation, but I'm skipping this. You can look at finally how everything comes to this, you know, how everything comes to this, right? So but then the problem is it's still continuous. We have not discretized this, so the next step has to be, we have to discretize this. So it's stable by construction, but it needs to be discretized. So that's why S4 came in. So this paper is the S4 paper, the ICLR 2022 paper. And what they did was they said that okay, we will take all the good things of hippo, which is A, H means A hippo, but we will take the normal form of it, right? The normalized matrix, which is A conjugate or A transpose is equals to A transpose A, so that normal form, and we will add a low rank matrix to that. What makes that happen is that when you move that to the Z form, you only get the lambda matrix to deal with, together with the low rank version of it, which is P tilde Q conjugate tilde, right? Where P tilde is V conjugate P and Q tilde is V conjugate Q, where V is basically the eigen matrix when you decompose A H. So instead of going for a plain simple eigen decomposition, which can be ill conditioned, as I said, that there is no guarantee of the lambda staying within the stability zone, if you do this, which is you do a normal plus the low rank, you then get something which is, you just work with the diagonal plus the low rank, right, in the Z form when you change the basis. So and then you discretize it, same technique, and you get and then you apply the FFT, again the same technique, and then in order to get the the Y back, you apply something what we call as you apply this fast inverse. The inverse you can apply via what is the Woodbury result, that the theorem, which is D minus U V transpose inverse is the same as D inverse plus D inverse U of U multiplied by I minus V transpose D inverse U whole inverse V transpose D inverse. But then it looks like quite a mouthful, but you are dealing with D inverse all through, so you just have to compute D inverse, which is very simple, which is because D is diagonal, the diagonal matrix, so it's simple to compute, and you are just dealing with V. You have already computed, because you have to compute B in order to compute D, and you can just do the inverse just by doing this plain simple addition. So the final contextual embedding would be this, and the S4 architectural pipeline is, you first do the U, you do a spectral filtering, which is using the FFT, but this time you are using the kernel as the A is equals to now the lambda, which is the diagonal matrix. You're just using the diagonal matrix plus the low rank, and then you may have a gate or some normalization, layer norm, batch norm, and so on, and then you finally apply a head and a residual, You can layer it up also, multiple layers if you want. You can do, and in each layer you do the same thing, and then put a decision head. That could be a language modeling head, which is an X word prediction head, or can be classification or whatever other kind of task head. And the performance comparison was that you so what they did in the paper was they compared S4 with other transformer based models, including linear complexity transformer based models, in terms of what? In terms of the speed and memory across different lengths. So they took 1024 length context, and then they also took 4096 length context, and then they tried to see how fast S4 is as compared to, let's say, linear transformation, which is linear transformations are linear time, and then they try to see how good they are. It's quite comparable as compared to the speed, right? And also quite comparable as compared to the memory, but much better than the normal quadratic self-attention based transformers. So the insight is that, in terms of the scaling behavior, the transformer complexity, it's much better than the transformer complexity. It matches linear transformers in speed, and the memory advantage. It also has a constant size state, because it just the A is time invariant, right? So it scores on that. And if you look at the long range arena performance, again, now this is more on the accuracy side of it. So you'll see that S4 is performing much better than many of these long context models like Big Bird, Reformer, linear transformers, and so on, right? And so that is sort of what we have for S4. Now, where the state of the art models fall short is, so if you take an example, let's say that you have this sentence: John promised Mary he would not visit Paris yesterday. And this is important. This is the final takeaway, sort of. So each architecture answers these questions differently, whether it is transformer based architecture or RNN based architectures or SSM based architecture. So some architectures remember too much, while others forget too fast. So that's the problem. So if you look at transformers, what's going on? So over here, every word looks at every other word. These are plain simple quadratic transformers. And if you look at these sort of models like MLA, GQA, group query attention, multiple multi-head attentions, and so on and so forth, you find, like what you find in DeepSeek v3, Llama 4, and so on. You find that they compress or share the key values to save memory. So these are the techniques that you have. However, if you look at sliding window attention, that's another technique which is also used in Gemma 3. It restricts the attention to nearby context. So that's how they achieve the performance. If you look at MOE, or mixture of expert layers, you use only a few experts per token, which is the actual active learnable, and the active parameters are a lot less than the overall parameters, and you try to make sure that every expert gets to understand which query to be given to whom. So the linguistic lens would be like, he can talk directly to John, but every word joins the conversation and can dilute the effect. So it's costly, and it can potentially be noisy. So RNN style, it's like, the idea is we read like humans, one word at a time, right? So, but then it keeps the running summary through time, but it suffers from vanishing or exploding gradients, which means it forgets long dependencies. So it tries to mimic how we read as humans, but it has this issue. So let's say that when when the word not comes in, like the original. So what is John promised Mary he would not visit Paris yesterday. So when the word not comes in, the memory of promise has already faded. So what are we negating is already forgotten. So the effect of not is not being applied effectively, right? So when we look at linear attention, so linear attention is we keep attention's awareness but drop its cost. So essentially it's we do the K transpose KV, but we apply some sort of uh, function over the queue, so that we sort of restrict how much of the queue we see, right? So Qwen3 next, kimilinear, minimax M1. So we reflect the softmax with kernel or delta net approximations. So that's your 5 over there. Achieve big O of t linear time inference, but we see that most variants remain structurally efficient, but semantically they don't know when they are, they don't have semantic adaptations, in the sense that when they are getting new and new words coming in the autoregressive setup, they don't know that, okay, what is the meaning of this word and how I should apply my phi over there in order to do that linear time inference. So it's like a speed reader, so it skims the text quickly but only partially catches the nuance of not or Paris. So that's what linear attention would be. Mixture of experts. I'm going through all this because these are all what you would be looking at, and then you might be thinking that, well, why do we even need to think about SSMs and S4s and all of that? So that's why I'm giving you a perspective. So the MOE philosophy is, instead of one big brain, we may use several smaller brains. So that's the abstract equation, if you want. So YT is equals to basically a summation of all the active experts for a particular U, like DeepSeek version 3 R1 or Llama 4, GLM 4.2, 4.5, sorry, Kimi K2. So these models all are small, work on this small mixture of experts, and each token activates a handful of specialized feed-forward experts. Scaling efficiency is there, but yet routing relies on static embeddings, not evolving meaning. So when you route to one expert with Ricard versus the other experts, the routing is happening only based on static embedding. You don't look at what is the new evolved contextual meaning of this upcoming word, and you don't try to decide on the basis of that. You look at, okay, which expert should I move this towards, throw this to? You look at what is the static input embedding, right? So that is the problem with most of these MOEs. So yeah, so it's like a newsroom of specialists promised, and the word promise wakes the verb expert. Not should wake up the negation expert, but they are independent of each other. These experts are not thinking as if like, oh, this has been activated first, so I should now be thinking in a different way, and so that doesn't really happen. So the experts don't talk to each other. So state-of-the-art models in terms of SSMs. S4, we just saw S4. The problem is, it's like an orchestra that keeps playing one rhythm even when not should invert the tune, because it's a forward-moving wave. So even if a not comes and tries to negate the effect of some previous word, the wave will keep on moving over time. So it's very difficult to de-amplify sort of the effect of certain things as this sort of negation words come in. So to in a nutshell, So this is the landscape, so to say. So the core common limitation is that memory is there everywhere. Everybody is trying to deal with memory. Everybody is structure driven, but not meaning driven. Okay, so no mechanism that decides dynamically what to keep or forget based on the meaning of the new word, contextual meaning of the new word, right? So it doesn't update or revise what it has done so far on the basis of the contextual meaning of the new word. Okay, so it's like once the momentum has been set, that momentum is so forceful that it keeps moving forward, that wave keeps moving forward. It's very difficult to change the course of that wave. So it's only that you can go with the wind and change a little bit on that wind, but you cannot completely change the course of the wind. So that's what happens with these models. So that's the reason why they came up, in this COM 2024 people, they came up with this Mamba model. It's a very, very popular model, and this should not take much time. Maybe I should just keep going, maybe 15 minutes. So S4, the summary of S4 is this, that you took a continuous SSM, which is AXT plus BUT, and then you make the contextual embedding of Y using CXT plus DUT. You discretize it at token rate delta and make it like that. You convolute it, which means you don't like the sequential memory. You make it as a summation, and then you don't like the summation. You think that there is a better way of doing that quickly, so you convert everything into a Fourier transform, right? So you look at this, instead of looking at it more from individual eigenvector point of view, you look at it from individual frequency point of view, and then you do the spectral filtering. But the limit is K is all data independent, because A is data independent. That's why the K will be data independent, right? A and B are data independent, right? So the dynamics do not adapt to token content. So what you do is, instead you do something very simple. So you say that, okay, I would want to preserve the stability and speed of S4, but I want to make the memory more selective. Okay, so, or rather, selective means input aware. So why selectivity? The linguistic intuition would be that the moment the word not comes in, I should be able to understand that, oh, this not is negating something that is upcoming, and also maybe changing something that has already happened. So I should be able to quickly readjust that. So named entities, let's say not, should quickly suppress some prior semantic commitments, the commitments that I already made. Now the moment I see not, I should again readjust that. And named entities Paris may need slower decay to maintain the discourse topic. Discourse markers like however should reweigh what gets carried forward, because you should, which means it's not just a token or a symbol. You should know what is the role, the semantic role of the word however. However is not the same as and. Both are connectors. And is also a connector. However is also a connector, but however has a very different meaning, connotation, which rather than and, right? So John promised Mary he would not visit Paris yesterday, so the subject long range link needs to be persisted. Negation pivot not should selectively attenuate visit over there, right? So when you say not visit, you should know that, okay, since there is not, now the upcoming visit has to be attenuated accordingly. So entity topic like Paris should persist moderately. Temporal cue like yesterday affects temporal interpretation briefly. So we want the model to adapt its memory update, which is A and B, all of that when these tokens arrive. So from fixed to selective dynamics. So this is the selective dynamic. What did you do? Just plain, very simple. Earlier there was no UT. So ये लोग नहीं थे UT. You just added the UT with the A and created a transformation. So A prime, let's say something like that. So instead of just keeping A, you create A prime, and A prime is always dependent upon the current UT that is coming up, right? So that's the thing. So the gears, which is the A and the B and the C, A would mostly look at the decay, B is the mixing, and C is the readout, which is the final embedding output. So you keep on reconfiguring that in terms of the UT. So in other words, like whenever UT is not, again your A changes to something else, B changes to something else, and C changes to something else. So then when you look at the diagonalization, and when you look at and everything else pretty much remains the same, then AUT would be minus lambda UT. You actually use a minus. Why? Because now you are adding a UT, which usually could be plus also. So essentially you try to make sure that if your diagonal lambdas are positive, so ultimately you want to make your lambda negative, less than 0. The magnitude of lambda should be less than 0, otherwise it can explode. So you keep the minus outside the matrix capital lambda, and then so that your lambda could be positive, so that your overall lambda becomes negative, because your negative is outside the matrix, right? So which means you just made a quick change so that your lambda could be now your lambda has to be positive instead of negative, because otherwise negative will become positive, and that's the problem. So your lambda IUT is now going to be a soft plus. You get the point why we did this slight trick by keeping the negation outside, because lambda, because when UT comes, you have to do something like a percentage. You have to create some sort of a percentage out of it, like a soft plus. So since that is positive, so that's why your negation has to be outside the diagonal matrix. So, and then you have some weight. Okay, so basically gates. So how to infuse your input? So you say that there is a WG which creates the gate GT, right? And then you have your lambda T, which is basically W lambda multiplied by UT. So it's a transformed version of, so there's a lambda gate. And then you have BT, which is WB multiplied by UT, which is that is what you will look at as BT. And then CT is WC multiplied by UT. And then what you do is you plug lambda tilde T into the soft plus, you get the lambda T, which is the eigen value of the diagonal matrix, and then AUT becomes minus, because the minus is outside, minus of diagonal lambda T, right? So that's how you get the thing. And then what do you do? This gate that you have, the GT, you now use the gate to hold on. Yeah, so basically then what you do, you have this update rule, xt plus 1 as a bar t xt plus b bar t ut, and you have yt equals to ct Hadamard xt. So for all diagonal a ut, which is minus of lambda t, a bar t would then become e raised minus lambda t delta t. Okay, so element wise it would be, for one particular eigenvector, it would be minus lambda t ti delta t, and your b bar would be an integration of that, which will be inverse of the diagonal matrix multiplied by I minus E raised minus lambda t delta t of bt. Okay, so the intuition is the bigger the lambda or the step, there are two knobs, means faster for getting on that channel, on that specific channel or that specific aspect for that particular token, right? So you have now these two gates, alpha and beta, and what you do is in Mamba is you apply the alpha gate, which is the forget gate on xt, and you apply the update gate, which is beta, on ut. Simple. This portion is simple. So it looks very, very close to something like GRU or even LSTM. So xt plus 1 is basically a forget gate applied on the previous xt, and the update gate applied on the current ut. Now the alpha, the forget gate, comes from E raised minus lambda t hammered delta t, which is this E prime t, and beta, which is the the update gate, is basically 1 minus that lambda t, alpha t, divided by lambda t multiplied by the bt, where bt is basically this is basically wb multiplied by ut. Now how does this derivation happens? I've given the derivation here. It's very simple. Is if you make a integration of e of raised lambda tau d tau, it becomes 1 minus 1 by lambda, right? And then again you substitute that you integrate that over tau is equal to 0 to delta, you get b equal multiplied by b, you get 1 minus lambda e raised lambda delta by lambda in multiplied by b. So that is how you get that update gate beta, 1 minus alpha by lambda. So that is how you are getting that that equation. So basically it's not just it's basically derived from the alpha only, and the Duhamel's form, closed form, the discretized form over here, the bar B. So the gated recurrence, the interpretation is that not lambda t spikes for channels tied to affirmative intent. So usko kam karna hai, basically you have to drop that down. If there was an affirmative intent, you have to drop it down the moment not comes in. When Paris comes in, lambda t smaller should be smaller for entity location channel, and alpha t should be higher for the topic, the place topic or the location. So that should go up. At yesterday transient temporal channel, which is, so you should moderate the beta t, which is the how much information should be when yesterday comes in, how much of that information, yesterday information, should actually get in. You should moderate that, and then that should also have a faster decay. So that should be forgotten after some time, the yesterday information. So pronoun he, again the state highlights the channel that binds back to John, so John should persist, otherwise that binding back won't happen. So why is the computation linear time? Because if you unfold it, this alpha, the forget gate with the update gate, if you unfold this update equation, you'll get this projection, right? And then what you can do is you can, if you look at this, I gave you an example why it's linear time, because at time point 0, you you knew nothing, right? So your projection would be just 1. The prefix, which we call as prefix, so that is just 1. And let's say your alpha t is 0.9. So your incremental update will be 0.9 of x0 plus 1. And then when alpha t becomes, let's say at time 0.1, when the new token comes in, and let's say that alpha t is 0.8 at that time, which is the forget gate is 0.8. So then your previous prefix was 0.9. You just look that up. So you don't have to, basically you don't have to look at everybody before you. You just look at whatever happened just before, just in the previous time step, right? So that's what makes this linear time. Okay. So if you look at the token condition kernel, is effectively kk, which depends on ut minus k via alpha, beta, and c. So this becomes data dependent, isn't it? Because your alpha is data dependent, which is the forget gate, your beta is data dependent, your forget gate, and your c, thereby your c is your data dependent. It keeps on changing as new information comes in, right? So it's a token conditioned kernel. It's not just a unconditional kernel. Everything remains the same. So if you look at S4, it's just that kk multiplied by ut minus k, but over here your k, what is the k over here? Whatever I have data dependent weight. So think of that as the Mamba k. That entire whatever is in brace inside the summation. Think of that as your Mamba k, the k for the Mamba. And that is multiplied by ut minus k, which is the same as S4. So the overall form remains the same. It's just that your k has become input sensitive. So the filter reshapes itself on the fly. So it ensures stability. So because soft plus, you're applying soft plus to get the lambda. So soft plus will always make it positive. So what happens is you and that's how your entire diagonal matrix will always be negative because of the negation that was outside. So step positivity, because your delta t will always be positive, so that is fine. So it's bounded because your alpha, which is the forget gate, is always going to be between 0 and 1, so it avoids the explosion. And there is a nice gradient flow. So your per step contraction curbs exploding gradients, right? Because of that alpha t, So the steps are: you start from the S4 stable backbone, diagonalize A with the decaying mode, specialize to diagonal A for fast per dimension recurrences, make ABC selective, right? And discretize that to get the gates, the forget and the update gates, and then apply the recurrence using those gates, and then do the algorithm of selective scan, which means you just keep looking at the previous alpha and the previous beta. You don't have to look at every single alpha that you have created before. You have to keep, it's basically linear. You just move forward. So the performance comparison was done on 8 zero-shot benchmarks like Pi, Lambda. We talked about that. Helaswag for Rakuf. What are those benchmarks? Compared against open source transformers like GPT-NeoX, NeoX, OPT, Pythia, Rakuf, etc. The goal was, does the linear time selective SSM match or outperform quadratic time attention? That was the goal. And they scaled this model, which is the Mamba, from smaller Mamba to larger Mamba. to see what is the effect. And so this was the evaluation over all these different types of at different sizes. So starting from 360 range models to 1 billion range models and so on, to 1.5 billion range models and so on, and they looked at it. And what the key highlight was that Mamba 370 million would beat Pythia 410 million and hybrid H3 360 million. Mamba 1.4 billion and 2.8 billion matches transformers nearly twice the size. These are accuracy results. And Mamba 6.7 billion achieves state-of-the-art zero-shot average, comparable to 13 billion GPT Neo X. So much smaller model, closing in to much higher, almost double the size transformer-based models. So efficiencies, linear time memory mechanisms are not just good for scaling, they also generalize quite competitively across all these baseline benchmarks. Benchmarks means these, like Lambda, Hellaswag, and so on. And if you look at the training efficiency in context, you see that the red one is what the linear time prefix scanning of Mamba is, and it's pretty much is linear, as the sequence length increases. Whereas for others, even including flash attention, it starts getting out of memory as you increase the sequence length in terms of the size, in the length of the history or the length of the sequence. But Mamba very nicely, almost linear increase when it comes to linear time increase scaling, when it comes to increasing the number of tokens. So for short sequences, all methods are more or less comparable. As you can see, like 512 tokens and all. There are a lot of techniques which are more or less comparable. But as the sequences grow, attention cost rises sharply while Mamba remains near linear. Flash attention 2 still hits out of memory beyond 256 while Mamba trains stably. And the scaling property is that the training time is roughly directly proportional to the sequence length for Mamba, but it's square that for attention. And the inference throughput, if you look at it, this was the result, like in terms of batch size and the throughput, which is the number of tokens it could process per second for different batch sizes. And over there also, Mamba 6.9 billion version is doing sufficiently well. And the insight is that as batch size increases, transformer throughput saturates early. It's not able to process too many tokens per second, that much. So Mamba scales almost linearly with batch size. Both small as well as the larger Mamba version outperform comparable transformers. And the reason being that there's no quadratic KV caching during inferencing, no exponential growth in memory. The state updates are constant size because it's just a carryover of the same state. You don't have to look back every time a new word comes in. And it's quite GPU friendly because you can do a lot of parallelization over the GPUs across because of the FFTs and all that you are applying. So summarizing, is 40x faster training than standard scan, the scan that was used for Mamba, the linear scan. 5x higher inference throughput than transformers, and it has a linear compute memory scaling. The qualitative insight being that it's efficient from selective recurrence, not sparse. You don't need sparse tricks, unlike linear time transformers or other kind of sparse attention kind of stuffs. You don't need, it enables ultra long sequences like more than 256,000 tokens without out of memory issues. It's streaming friendly, ideal for autoregressive tasks, and so overall Mamba combines long range reasoning with transformer level performance, but it runs at linear speed and stable memory. Okay, so that's the deal. Any questions? You have to internalize SSMs first. Take your time to internalize that. Then you need to internalize S4, and then only you can internalize Mamba. Once you have internalized S4, a Mamba is easy because it's just a gated version of, if you look at it from that point of view, it's a gated version of S4. So yeah, so it's alternative. I wanted to also discuss CAN, Kolmogorov-Arnold networks, but maybe next time. That's also a very interesting alternative model. But Mamba was something that got picked up a lot, and a lot of variants came out, like Jamba and all, out of this. So there was a lot of traction for Mamba. So I thought that we should do that. So there's one final point I want to make, is that there's no one fit all. There are different use cases. It's not that, oh, you should forget transformer based models and use Mamba style models. It's not like that. Different use cases will need different types of models. If you want to model really complex long horizon input, sequential input, long horizon, very long horizon, and very, very complex, then probably something like state space models will help you more. Like let's say user interaction trajectories, not just language, but a lot of different types of clicks and skips and so on and so forth. Let's say some user is going through YouTube shorts across a week, a whole week, and sometimes he's clicking, sometimes he's skipping, sometimes he's clipping and watching it for long, sometimes it's not watching it for long, and even skipping. Sometimes when the user is skipping, one can be that he doesn't like it, another can be that she has got a better option, alternative, another can be reason that she has already seen that and that's why she is skipping. So it's not that she's not interested in it, but she has already seen it. So your trajectory tau could be, unlike language which just has a linguistic drift, so this is a behavioral drift. It's a very complex behavioral drift. So if you have to model those sort of things, that probably SSM sort of models will work better. But the thing is that you should study in a way such that you understand the use case first. For very shorter sequences, you don't need this complex models, because as you saw that for shorter sequences, there's not much of a gain or anything like that. So transformer based models are pretty much fine.